Okay. So these are actually, oops, sorry. These are good because they take a running start at those 3 different types of spectra, continuous. Okay? Kirchhoff's first law, no lines. Okay? No lines. His second law was the bright line. Oh, sorry. What am I missing now? I'm going to see what that block is. Like, really? There. That's a prism. That's important. Okay, so bright line looks like this. And I don't want you to forget about the whole what electrons are doing. Okay? So with continuous, there's no electrons to worry about, per se. Okay. But with emission, basically, you get energy because electrons are stepping down from a higher to a lower energy. So what do you think when we saw the neon in the lab? Emission? It was emission. And for every emission line spectra, there is an absorption line spectra that would match it for that particular element or compound. That's the third law, exactly. Sometimes I call this dark line. Doesn't it look like kind of like dark line spectra? And so when we saw that that thing with the kind of the picture with that looked like a rainbow with lines in it, that was dark line. That was absorption line. Yep. And like this said, it's tried to kind of be descriptive down here. This happens when electrons jump to excited states. Okay. Well, we keep talking about these different like electrons can be here, electrons can be here. And so finally, when we see these blue lines, these are all possible like energies that an electron can be at. Okay, so this is kind of as I've been doing my hand, that's the blue lines. And you see kind of the arrows, in this case, all going down. So these would be what kind of emission? These would be giving energy. And the way this works is, let's see. This is all that one little electron around a hydrogen atom. I think later on I tell you, but this actually is in visible light. This is in ultraviolet, and this actually is in, I think, infrared. Those are the different cousins we see. So lines can be, fingerprints can extend out, not just visible. Okay, so this is the same thing of hydrogen. This thing over here says potential energy levels. Okay, so these right here, you see those kind of down, those, what are there, 4 down arrows that are called 410 nanometers, 343 nanometers. Those are wavelengths, nanometers. Of course, you recognize meters is a length. And nano, like you saw a few slides ago, is just a metric prefix. It's just a very much a fraction of a meter. So these are all lambdas. Okay, these are all just, that's supposed to be my wavelength. And can you see the, let's see, there's the 656, there's the 486, 343, and 410. Of course, it looks like it's got a pair of them about there. So, oh, I had that wrong, sorry. The previous slide, I said that this was infrared, and this really is ultraviolet, shorter wavelength. So we won't see these, okay, and these are infrared. Does that all work for you? So now I circled something at the top there called ionization. This is a kind of a fun thing, and it happens all the time, especially at hot temperatures. Basically, in normal atoms, they're like, how do I say this? the protons are in the center, okay, and mostly around those atoms, however many protons you also have electrons, okay? Like for helium, there's what, 2 protons, and there's usually 2 electrons, okay? For carbon, there's always 6 protons, and there's usually 6 electrons. And the beauty of that is it keeps it what we call neutral, no charge. But here's the deal. Those electrons outside the nucleus, there are times when basically they can be stripped away, and we call that ionization. So that's kind of what this is saying, is basically it's left the building. Okay, it's left the possible energy levels. It got so far away that it's no longer associated with that nucleus. Okay, electron was stripped off. Okay. Did you need anything on that slide? It looks similar to me. So I like these little animations too. Let's see, one of my favorites. We're going to see light sucked in by a gas. Okay, so what this is trying to, you see all the colors of the rainbow going from the light source into the telescope. Okay, that down here is Kirchhoff's first law, continuous. Okay, I'm going to add a gas cloud. So I added a gas cloud and see that based upon what was in the gas, it is sucking particular colors. Which colors? Well, these particular wavelengths, those particular colors were sucked. Why? Because it was a specific gas in that cloud. It's a fingerprint to tell us what that cloud is. Okay, so what sort of spectra do we have down there at the bottom? Is it absorption or emission? Absorption. It's absorption.
I can't even say the word.
Let's see. Now the telescope's over here. I'm going to keep the gas cloud there, and I'm going to move the telescope over here. Okay, so now the telescope actually isn't in the line of sight of that star's light. Now look what it sees. It basically just sees the kind of crumbling miscellaneous energies that are given off as those electrons fall down that were promoted. So can you see the negative now? Okay, so what kind of spectra do we have here? Is it absorption or emission? Emission. It is emission, yeah. That's cool. Okay. All right, so let's look at some spectra, I guess it'd be. There's helium, sodium. Have you ever taken chemistry before and they took sodium chloride? Well, okay, maybe you should. You can take something like table salt, and if you put it in a flame, it'll give a certain color. And kind of what we've been talking about is why it's that color. Okay, it's a flame test, and it has to do with how the electrons are configured. Neon, does that look familiar? Kind of lots of red. Okay. I think we're okay. All right. Fingerprints. It looks complicated to me, so I'm not going to have you, what we say, interpret spectral lines for your test. Okay, you just need to know that they're out there and they can be used to understand what chemical elements there are. All right, come full circle. So, what do you think? Is this absorption or emission? How many people think absorption? It's absorption. Why is it absorption?
I don't negative. That's all I got.
Negative?
Yeah.
Because why?
The dark bands.
The dark bands make an absorption. Yep.
Okay.
Okay. We did this recently, so I'm just going to kind of put it up there. So remember, this is what I said, this is like what Mars would be sending us. And we're like, okay, that's cool. So what do we have here with regard to this line? We have emission here, We have continuous here, we have absorption here, more continuous and absorption over there. All right. Oh, here's one for you. Have you ever done this trick? Okay. Or you take an object minding its own business, a poker, okay, that is not hot, it's room temperature. But if you heat it up, it can begin to glow. Okay. So, for instance then, if you take this poker and put it in a dark room, you're not going to see anything. If you take this poker and put it in a dark room, it's going to ooze out light. Okay? And so that oozing out of light is no small thing. Okay, so actually, cool objects and hot objects, like the cool poker and the hot poker, they actually, if you could take a look at all that energy that's coming from them, the distribution of energies will look different. And that's kind of what this is showing you. So right here, these are, can you see the blue curve, the yellow curve, and the red curve? The blue curve, the yellow curve, and the red curve. Those are 3 different objects that are sending us some information. Now, notice this is kind of like the same deal we looked at before. If you look along the x-axis, it's wavelength, and you look along the y-axis, basically it's intensity. So we have wavelength along the x-axis. Do you see the Roy G. Biv going backwards? Wavelength. And then just call this intensity. So the other thing is, this is the hottest, the blue one, and this red one down here. So the blue is the hottest. This one, this red one, this inner one is the coolest. Coolest. So 3 different objects, 3 different kind of, they're like signatures, basically. So 2 things we can talk about with regard to how hot an object is and kind of what its signature is going to look like. The hottest ones are going to be, do you see where it's the tallest on the intensity? Okay. The coolest one's the shortest. The other thing about the hottest one is the peak, which is right here, is shifted over to the shorter wavelength. Shorter wavelength. Do you see those 2 things? The hottest, tall, that way. Coolest, short, the other way. Okay, if I was going to kind of identify the peak of that one, it's short and it is to long wavelength. That's kind of the trend. So honestly, this in a nutshell is how astronomers can go ahead and focus on a light, go ahead and get the pattern of energies coming from that light and say how hot the surface of that star is. I said a star. You can focus on a star. Okay, get the energy coming from that star, throw it up there, and understand what the surface temperature is. Okay. I think that's cool. And it's, you know, it's a little different topic than the whole spectral line thing that we've been talking about. Oh, I forgot about this one. Isn't that adorable? This is our little profile. Okay, so it's clearly in infrared, right? Okay, and we talked about temperature scales, right? We talked about the Kelvin temperature scale. So we're about 310 Kelvin. Aren't we adorable? So we're short. Okay. So just to kind of summarize again, the hotter an object, the more light it emits. So that's like up on the y-axis. Okay. And not only is it higher on the y-axis, but it's over to the shorter wavelength. Let's see.
How do you make the little wavelength sign?
The little wavelength sign is, it's called lambda. I usually start with that part, and then I kind of draw an upside down V. So I kind of have the tail first, and then do the slash. Yeah. Did you know, like, I heard they're going to stop teaching cursive to kids in school?
My kids said that.
I know, that
Seventh
is
grade.
No.
They don't use it anymore.
Did you say, so it started or whatever?
Yeah, that's what they don't. 10th grade, or in 7th grade, and they're not using cursive.
Because, you know, as adults, you sign your signature and you print your name. So how will that look? Give them your digital thumbprint or something? I don't know.
Pretty soon then we won't write it all, you just type on the computer.
It is sad.
That's pretty sad.
Okay. I think we're okay with that one. Okay. So do you remember the other day when I was talking about perihelion and aphelion? I went, remember that? Okay. So that's kind of what reminds me of this idea called the Doppler effect. So what we've got here is a train. In the case on the left, the train is sitting still. In the case on the right, the train is moving to the right. The other parts of this is we have somebody who has a listening ear, okay? And in the case of the moving train, the train is moving toward that listener. Okay, oh, I guess we have two people. Okay, one on either side. So think of those little squiggles as being kind of the pitch that the train is emitting, okay? So when the train's sitting still, you have people on either side, and they hear the train go, you know, just kind of humming along. What's that?
I'm sorry. Does anybody watch The Big Bang Theory? Isn't that what he was talking about when he was wearing his like Halloween costume? He goes.
Probably.
I'm sorry. I just thought of that to myself. But he goes, hold on. I'll try it again. I'll go slower this time. Like, what?
Definitely.
I love that show so much.
I've watched some episodes. It is good.
It's ridiculous.
The Doppler effect, exactly. So when, is it Sheldon's head was coming towards you, it was going like, and it was going to go, so what happens is, you see these squiggles are getting shorter for the guy who's on the side where the train's coming, the pitch will actually get higher. And we hear it all the time if you have a kind of car that's coming towards you. The pitch kind of goes higher, and then it goes faster, and the pitch goes lower. So kind of, it's almost kind of makes sense if you think of them being squished together, those little sound waves as it's coming towards you, and then lengthening as it's going away. Pitch goes down. I love that. Well,
So you have like one solid white dot in the center or whatever.
well, instead of sounds, we're worried about emitting light. Okay. So this is similar. It's not a train, but it's a light bulb. But you do see an observer on either side of the motion of the light bulb. So it's really kind of supposed to be analogous. Okay. So here we have a light bulb, and that light bulb is moving towards the right. So the deal here is this guy actually will see the light bulb at a shorter wavelength. Okay. Like how does that work? Well, I'll kind of show you an example of how that works. This guy over here will see the light bulb at a longer wavelength in general. Set of wavelengths, I guess I should say. Shorter set of wavelengths, longer set of wavelengths. Do you remember like way back when we started this class? It seems like we've been doing this forever, doesn't it? We talked about the fact that galaxies are all moving away from us. What we do is we see a what we call redshift. Okay, galaxies are moving away from us in general. Not the Andromeda galaxy, but they're receding, and they are with that motion kind of having a lower wave, lower pitch, but it's not pitch; it's electromagnetic radiation. Okay, so the redshift if an object is moving away from you, and what we call blue shift if the object is moving towards you. Which kind of makes sense because red is a long color and blue, indigo, violet, but that's a shorter color. So, red shift, blue shift. I always think of the Dr. Seuss. One fish, two fish, red fish, blue fish. Something. talk here. Okay. So, for instance, I'm going to kind of show you the shift. And I'm going to show you shift in the set of wavelengths that are emitted. These are emission lines, okay? So these are normal emission lines. And see if you can kind of detect the movement. If you compare the first one to the second one, can you kind of see them going towards the, yeah. And notice it says it's moving away. And the third one, moving away even faster. So I'm going to clear those off, and now we're going to actually look at shifts where it's a set of spectral lines are getting shorter wavelength. Shorter wavelength. I like this one's my favorite because this one, so this would be something that is moving towards you. Okay, shorter wavelength, blue shift. That way, yeah, moving towards you. I like this one because it kind of changes color with it. But here's the problem with the whole shift thing, red shift, blue shift, is that it only works with what we call radial motion. So it's sometimes called line of sight motion. Okay, so the opposite of radial motion is proper motion. And proper motion, it does not work. So in example 1, we could see if that yellow orb was moving away, we could see that motion. Okay, that's called radial motion. But object 2, do you see if it was kind of, from our perspective, moving left and right? We couldn't see that motion using the Doppler effect. Okay, we could, some other effect maybe, kind of see it move. Okay, but the Doppler effect wouldn't work. And then like this slide says, a lot of times, the 3 actually has a little bit of radial component and a little bit of proper motion component. So we could see the radial but not the proper motion. Yeah. What's the next slide? Oh, good. Well, that brings us up to telescopes, and that's where we will start next week. We'll be fine. We'll fit it all in one way or the other.
So do we still go ahead and do our questions?
Yeah, no, so questions will not be due. You can go ahead and work on them, but they won't officially, I won't collect them until, so, okay? All right, so just to